Hello folks, and welcome to the first video here that we're going to be doing on the Tesla Model 3 inverter. The victim that we have on the bench here for you today is the rear drive unit inverter from a 2019 Model 3 European left-hand drive vehicle, originally purchased, I believe, in Germany. It only had about 20 or 25,000 kilometers total driving on it when it met with an unfortunate accident. So our mission for this particular project, should we decide to accept it, which rather stupidly I already did, is going to be to get our drive unit running in such a way that we can run the system outside of the normal Tesla world, so not running it in a Model 3 but rather in a EV conversion. Now I'm just going to talk a little bit about some of the various methodologies that others will probably use, that I could probably use, and then we'll dive right in here and I'll show you in today's episode basically the overview of what we're going to do, and I'll show you the first few stages of that. Now, for those of you that may not know, the Model S and the Model X large and small drive units, I had already designed a replacement logic board for them based on the open inverter system. And that's been working quite successfully, not only in my own car but in several others throughout the world. Now, the enabling factor for that, to do that, was that in those particular drive units, Tesla used a separate logic board for the logic functions and a separate board for the power functions of the inverter. Because what we're trying to remember here is that these things are just inverters. They're just 6 transistors and a capacitor, bit of driver circuitry, a bit of protection circuitry, and some current sense. That's it. You know, there's no real magic here. But so what we were able to do there was basically to remove the head of the inverter, which contained Elon's brain, and basically replace it with a Johannes brain. Now, obviously this is the first time that I've had a Model 3 drive unit here to actually work on. But prior to this, I'd seen some videos on YouTube and various photos, and I'd been quite interested in, you know, how they were doing this, just from a general engineering point of view. I'd been quite interested in, you know, how they developed this down onto a single PCB, which you can clearly see here, and on the surface of it, that would mean that we could not employ that particular strategy that we had used before to, you know, take out a particular board here, reverse engineer that, design a replacement based on open inverter, and then throw it back in there. That would not really work for us. I then, you know, kind of thought about this again and again, and obviously this device here is the brains of the whole operation. So in one sense, this microcontroller here is the logic board. It's got all the logic functions in there. and the rest of the board is basically things like power supplies, inverter drivers, gate drivers, current sensing, la la. So one idea that I initially had was, okay, I'm going to take that device off, and I'm going to design a PCB with kind of half, what do they call them, castellated holes around the edge. And then I'd have a little PCB that would basically drop in onto the footprint of this guy here, and would contain a little open inverter brain. Now, I've gone away from that idea, and actually seeing the board here, I'm really glad that I have, because I think, without some very complicated and expensive kit, I think we would suffer trying to remove that device from the PCB. So, other options then that I considered was, trying to reprogram the device, because there is what I'm assuming is a JTAG connector here, this little white. I shouldn't be using my big stumpy fingers. When I get a screwdriver for you, it might be a bit easier to see. There's a little white connector here beside the main device, so I'm going to assume it's a 6-pin, I think, if I'm not fantasizing. Or is it it's actually a 10-pin. So that's probably a 10-pin JTAG. So option would be, again, we'd need to extensively reverse engineer the connections to the device to figure out what pin does what. And then we would go ahead and, reprogram it with some open source software that would control our motor. Now, I'm not a software engineer. I dabble around a little bit, but my formal software training kind of petered out with 6502 assembler. So also, that means then that it's something outside of my control, and it just brings in other potential failure mechanisms, I suppose. So next plan then was, okay, we can't pull the chip off, we can't reprogram it, so what are we going to do here? Third option was, okay, what if I were to probably get somebody to write a very simple program that literally just woke up the device, configured all the pins as being inputs, and then put it in some kind of a sleep mode. Then potentially we could go around our logic board here, figure out things like the gate driver chips, the current sensors, the power supply, the resolver exciter, the CAN transceivers, all that kind of thing, and inject our own signals in there. And I was all set to do that. I was searching around the web for people that knew how to program these Texas Instruments chips, and then I was looking at the data sheet one day, and kind of had a bit of a duh moment. It's like, duh, hello Damien, duh. So what happens with a microcontroller, and this is just a microcontroller, it's a very powerful one, but it's a microcontroller, it's got power lines, it's got a crystal here to provide clocking, and it also has a reset circuit. And what would happen if we were to simply hold the device in reset? Well, the very same thing as if we'd gone to all the trouble of reprogramming it. And so looked up the data sheet, as I said, and on this particular package, it's pin 124, it's called XRS, which is the reset pin. And the data sheet recommends tying that to the 3V3 line with a 2K2 resistor. So I went in there, scraped away a little bit of the musk goo, and measured the resistance from that pin to the 3V3 line, and guess what we find? 2K2. So then soldered in this little bit of red wire that you see here. We'll show you in a few minutes what actually happens when we pull that to ground, but it does, as you might expect, and it basically holds the micro in a reset state. And from what I can see, I'm not 100% sure, but from what I can see, just with a bit of very, very early probing around here, the pins go high impedance or inputs, or just don't drive or whatever. And that's an ideal circumstance for us. So obviously our first target here is going to be to looking at the gate driver chips. And I'll show you the data sheet for those soon, but there's a pin on there. I think it's, I'll look it up, I think it's pin 11 on those. That is the shutdown pin. So obviously, you know, when we power this up sitting on the bench, it's not getting any of the CAN or the, you know, the kind of things that it wants to see. So it's shutting off all of the gate driver chips, and it's pulling all of those disable lines low, which basically disables the gate drive. Now, when we, as I call it, putting Elon here to sleep with our reset line, all of those shutdown signals jump up to 3.3 volts and the gate drivers come alive. So looking at this, we could well be on to something. Now, before we jump straight in here, I am going to just cover one thing, because I know this is a question that we're going to get asked. It's going to pop up, and that is, why are we doing all this? Why are we messing with the hardware here? Why are we not just injecting the CAN that this controller wants to see and running the motor as it was intended in a Model 3? Well, there's a couple reasons for that. First one is that obviously we have no info at this point on what the CAN messages would be. I have some Model 3 captures, and if it was a simple thing whereby we're looking for a certain enabling sequence to go into the inverter to put it into drive, neutral, reverse kind of thing, because the throttle signal is still analog hardwired in here. So in theory, we would give it 12 volts ground, high voltage throttle signals, and the CAN that it would expect. Now the problem here is that, just like the Model S and the Model X stuff, there is, to the best of my knowledge, and I say this because I don't actually know, there's so little real info out there, it's just supposition. You hear something on the web, some guy says something, another guy repeats it. Is it real? I don't know. Okay. But there is some level of encryption between, obviously, Elon's brain here and the other modules in the Model 3. So I'm guessing it's some kind of a challenge response, encrypted messages that have to flow back and forth before the drive unit will enable. And the information on that, quite naturally, is a closely guarded secret within Tesla. Now, there'll be people that will work this out. There will be control systems available based on that. I have no doubt about that at all. You know, they'll either do it by brute force, they'll do it by having inside info within Tesla or disgruntled employees, or they'll reprogram the device, be it with the CAN bootloader or with the JTAG, or to be honest, I don't know. Okay, I don't know what people are going to do with this, but it'll be very interesting to see. Now, let's say that I could just snap my fingers here and know that stuff. So I now know the encryption and the canned messages and all that. Now, obviously, I'm not going to tell everyone else because then in theory, Elon goes off, changes whatever seeding is in the encryption, and I'm dead. You know, it's not working anymore. Now it becomes, what firmware do I have in here? When did my car, you know, when did the car crash? Did it have a certain firmware? Do I have to change the firmware? And all this just turns into, at least for me, something that I don't want to get involved in. So instead, what we are going to do is we are still going to use our open inverter system. We're going to use the same mechanism that we've used with success on the previous Tesla Drive units. Excuse me. And what we're going to do ultimately is we'll have our inverter here. We'll be putting Elon's brain to sleep. He does a lot of hard thinking anyway, and thus, you know, let's give the guy a break. And the approach that we're going to take is going to be a hardware approach, and we are going to use the same, I guess, protocol that would have been used in the day of game console modifications. And how that was done typically was with a mod chip. So I just got a little blue pill board here, and something like this, something about the same size as this, we're going to design specifically for these Model 3 inverters. We'll have all the necessary bits on the board that we need, like Wi-Fi and whatever little bit of signal conditioning. And this little chip will just basically sit in here in the middle of the board somewhere. We just stick it down with whatever sticky pads. Very unprofessional, Damien. Yes. And we'll have about 10 or 12 wires come from this device to various points around our inverter board. We will still use the I/O pins here on the connector. We will reuse things like the resolver exciting amplifier, the CAN transceivers, the gate drivers, the current sensors. Basically, we're just going to mod chip the Model 3 drive unit so that we can control it, not Elon. So I'm not going to get into any more about this. I've blabbered on here now to a point that, you know, most people will have probably tuned out a long time ago. So this is the way we're going. It is subject to change as I find out more about the inverter. Understand that's not going to be to everyone's liking, but that's too bad because this is my version. Okay, I'm going to do this my way. Whether that's right or wrong, only time will tell. And in this game, there's many different versions of right and wrong. So if you're somebody that, you know, has a solution that uses CAN or reprogramming the processor, or that, you know, by all means, crack on. There's more than enough EVs, Teslas out there for everyone. So, all right, I'm going to get set up here. I'm going to get rid of my silly face from the corner of your screen. We will focus in on the inverter and have a little bit of a talk about how this roughly works, because I don't know the full story here. and we'll do a little bit of initial reverse engineering work, and I'll cut this video then, because as I said, I don't want it to be 3.5 hours long. So stand by for action. Alrighty, so here we are at our inverter, and we're in a powered up state now. So in order to do that, we need to supply 12 volts to 2 pins on the connector and a ground to the inverter casing here. Now, for those of you that might be interested, there is a pinout of that connector on the GitHub repo, and there'll be a link in the description to my GitHub, where I'll publish a lot more info on the things that I find out about this inverter. For those of you that are looking at the CAN control element, I did capture some CAN from the inverter here yesterday, just about 10 seconds worth, and there's 2 CAN buses actually on this system, and I have published those captures up on the GitHub as well, just in case they might help somebody, or indeed myself, possibly at a later date. So, okay, right now the activity on our board here, let me turn off the light, I don't know, it might help you see this, but we've got 2 LEDs here that are flashing alternatively red and green, probably about 100 millisecond intervals. And here, just on one of the gate driver chips, we have a red LED here that's on constantly. Now, the red wire that you see here is connected to pin 124, which is the XRS excuse me, pin. And I should have a wire here, I do, for ground, and if I just connect that wire to chassis ground, oh, come on, there it is. So we've got a couple things go on straight away. The first that you'll see is these 2 LEDs go out, and the current consumption drops from 150 milliamps to 100 milliamps. That is at 14 volts. The red LED here on top of this gate driver chip remains on. So what we're going to do next, get our light back on so we can see. So what we're going to do next is we're going to start having a look around some of the pins on the control side of this first gate driver here. Now, there is another video, well, there's a few videos out there, but on a channel called, I think, Engineer X, where he, about a year or 2 ago, did a very detailed look at the insides of one of these inverters, and he actually published a list of the main chips and integrated circuits on that, so it's very worth a look. And actually much probably better quality than my crappy videos too. I mean, I'm basically shooting this with a webcam. But at a first look, what we have here is we have the input, I should say the communication pins here. It's a 30 pin connector, 3 rows of 10 pins. There's some signal conditioning here. There's a few devices here which we are going to identify shortly. There's the main TMS 320 microcontroller here. It's a power supply section here. I'm not 100% what goes on in this part of the world, but it could be a resolver amplifier possibly, so we'll be checking in on that. This area of the board here then is entirely the gate drive for what I believe are silicon carbide MOSFETs in here. Now what I will do is I have ordered a cheap and nasty endoscope camera. We'll have a look in underneath the board when that arrives with predictably bad quality video for you. So what we'll do is we will have a look now at what some of these devices around the signal conditioning area are, And then we're going to have a look at this guy here. And I think that'll probably do us for this video. As I said, I'm going to try and break this up into kind of discoveries, and that we also have for you the front drive unit inverter, which does at first glance look very similar, but we're going to concentrate on the rear drive unit inverter first, because I think that's probably the most commonly available one. So again, we can see here, if we release the pull down on that reset pin, the micro simply restarts, and we're back up to 150 milliamps of current consumption. So let's go ahead and kill off the power supply, and I'm going to go here now and we're going to have a look and see if we can ID. I mean, I'm just interested primarily in what some of these devices here are, because we're going to look to hijack as much of the hardware on this board as we can with our little mod chip. So the less that we have to add to this, the better, and the more that we can use of Mr. Musk's design, so much the better for everyone. So I'm going to have a look in here and see what I can find. The first victim here is U12, and of course it's upside down. So let's go ahead and carefully rotate our inverter around a bit without ripping things apart and getting everything out of camera shot, of course. And we go in a bit so that you guys can see. Don't think I've managed to wreck it just yet. Okay, let's go have a look. Get my big head in your way here. Seeing through the Elon goo is a bit of a practice start. So it's a Texas Instruments part, I can see that much. I'll get rid of the desk light here. It might make me see a little bit easier. Okay, the numbers are 1040AQ, 85K on the second row, is a Texas Instruments logo, and then on the bottom CC9PG4. So 1040AQ is the number that we're looking for U12. So I'm going to jump on another computer here now and see what 1040AQ finds me. And this is kind of the drudgery of reverse engineering. Okay. It is an SN65HVD 1040AQ EMC optimized high-speed CAN transceiver. So that is really good news for us. This is a CAN transceiver here. So we will be able to hijack that little guy for our CAN needs. And oh, this is interesting. So I'm going to have a look at how all this works, but it looks like pin 1 and pin 4 are transmit and receives, which we would want to hijack, and that's cool because at least one of them has a via on it, and the other one is heading off probably to some other layer under the board. So we'll be finding out about that another time. So okay, U12 is our CAN transceiver, so that's great. Let's see what this kind of biggish dude in the middle here is. Okay, this is an on semi part. TCA 0372. Okay, let's see what that is. TCA 0372. TCA 0372. Enter. What have you got for me, Mr. Google? Oh, okay, this is a 1 amp output operational amplifier. This is our resolver amplifier chip. All right. Okay, that is really cool because so U19 is our resolver amplifier. And let me see, U12 is our CAN transceiver. So looks like, you know, these are two devices that we're going to be using my stumpy fingers again. This U12 is our CAN transceiver and U19 is our resolver amplifier. So there's two devices straight away that we're going to be connecting to. So let's have a look-see here now. Let's see what this U9 has to say for itself. There will probably be a LIN transceiver in here too someplace, because this guy uses LIN to communicate with the electric oil pumps. That'll be another little thing that we'll have on our logic board. Let's have a look and see if we can work out what this guy is. Okay, can kind of see him. I'm gonna have to turn off the light again, sorry about this. Get the big head in there. I'm seeing LMV 844. LMV 844. Let's see what LMV 844 has to say for itself. LMV 844. It is a precision op-amp by our old friends at Texas Instruments. I wonder, is that signal conditioning for the resolver? Could well be, because my guess is that they don't use a resolver to digital converter on here. I'd say this TMS 320 is more than powerful enough to do that itself. Fortunately, our trusty STM32F1 can do it with Johannes code. So, okay. Let me just pause you guys here for a bit, because I'm going to make some boring notes. Okay. So at this point, I've secured my little reset line here with some tape. And I've just confirmed as well that pin 11 on the driver chip is the shutdown pin. And that should be pulled low to shut down the relevant gate driver. Now, the other thing that we're going to be examining as well is that these gate drivers have SPI bus capability on them. Just having a look with the oscilloscope on the SPI pins, doesn't seem to reveal any activity, but we're going to have a better look at the data sheet and see what that is used for. But at the minute, we're just probing around here, just familiarizing ourselves with our inverter. I'm going to just stick something under this part of it here, because it's just trying to roll around on me a bit too much. There we go. I'm going to put my meter probe on pin 11 here, and we're seeing, I don't know if I'm going to be able to see the meter too well, but there we go, 181 millivolts. So I'm going to use my shutdown on the Elon brain. And there we go, we're up to 3 volts. Now, to keep in mind that with the ground reference that I'm using for the multimeter, there'll be a diode voltage drop in there. So that is probably going to be about 3.3 or 3.4 volts. Then when we wake up Elon, he shuts the gate drivers down again. So I'm going to move over to another gate driver here and see if I can get on its shutdown pin as well. I have had to scrape away some of the musk goo. But there we can see our next gate driver chip, 181 millivolts on that pin. We shut Elon down and he goes up to 3 volts, wake him up again, and we're back down pretty much to ground. So definitely it looks like putting Mr. Musk in here to sleep is letting us potentially turn on our gate driver chips. Now, I had a thought as well as to what this stuff here is probably a gate power supply. So it'll be quite interesting to see if that power supply is running by default. It may not be, so that is something that we will need to find out. This power supply may, I've seen in some inverters, I've seen the power section driven from the main microprocessor. Kind of hoping that's not done here. That would introduce possibly just another level of work that we would need to do. So let's have a look and see if there is anything on the gates of our transistors. So we need both of our multimeter probes now, because these will be isolated power supplies. They won't be connected to the normal ground that our 12 volt system uses, because that would be very bad. Let's go have a look. I'm getting some sharper multimeter probes too, because these are way too blunt for what I need to be doing. So let's see here, Mr. Musk. We have BL1, BL2, BL3. So these are our phases, B, C, and A phase. These are our lows, and these are our highs. And I'm assuming these are our typical push-pull transistors that you see used to amplify gate drive signals. So let's see if there's anything here that we can find. I'm guessing these. So let's have a look here and see. So this is a 120 ohm resistor. Looks like that is potentially going to a gate. These may be gates here. Actually, this one I don't think is populated. Maybe it is. Maybe there's definitely two coming up through here. So let's see if there's just any voltage, even just looking at these here, and there's nothing there. So they may well be either just clamped off, or maybe I'm probing around the wrong pins here. I'm not really 100% sure. There's nothing there. There's nothing there. So let's see here. If we were to pick a phase, let me see, a phase would be in the middle. So let's pick a phase. Let's pick this one. See if there's any voltages that want to jump out at me. There isn't. So what we'll do now is we'll come back to our gate driver chip, because we do have a pin out for that. And we will see if the power rails that this needs are enabled. So on this chip here, VH is the positive power supply. It should be on pin 17. And there should be a VL going around here somewhere, I think. And there is, yeah, VL is on pin 23, which is our low negative power supply, or ground for high voltage section. So 14 and 23, 13 is the high voltage ground. So if we go from pin 13 on our device here, let's say to pin 17. So ISO ground is basically this this pin here. This is our ISO ground. It's this guy here. Just going to remove a little bit of musk goo there for me. What did I say? Pin 17 was the high voltage, or the high side power. So let's just scrape away a little bit of musk goo. There might be a via going around here or not, but we will find out in due course. We'll just scrape some musk goo. 13, 14, 15, 16, 17. It should give me enough to, just enough to get a probe in there and see if there's anything going on. Let's see what we get. Don't worry, I won't give you too much of this. I know it's super boring. But I've got to bore you guys to tears some days. Like, I can't have you excited all the time. Okay, so I have got nada, 0. Okay, so we have no ISO power rails up and running here, from what I can see. At least not on this chip anyway. Yeah, we got nothing. So it looks like our gate drive power supply is being shut down, which you would kind of expect, because 150 milliamps with the processor running is not a lot of power. With this gate power section running, actually making PWM, I'd expect to see over an amp of current from the 12 volt system. So we are going to have to backtrack a little bit through here, excuse me, before we can get into running our gate driver. So what I'm going to do, folks, is I'm probably going to cut it there for today, because there's probably more than enough footage of me being a muppet here for you. So things we've found out today are we can shut down the TMS processor. That does enable the gate driver chips, at least on their driver side. On the far side then, it looks as if the power supply section for the gate drives themselves is not enabled by default. So we're going to have to look at how that works. We'll have a probe around that power supply section, but that will be for the next exciting episode. So we leave you there. Whatever you do, please don't forget to dislike, do not share, and if you're subscribed to the channel, unsubscribe as quickly as you possibly can, because why would you want to watch this kind of garbage? I do not know. So I will put links in the description to the GitHub, where I have the repo for this and other projects, so do feel free to have a look through that. Also, there'll be a link on the in there for the Open Inverter forum, where I'm kind of detailing again this and other projects. And also, finally, in there will be the old PayPal and Patreon, should you wish to financially support my craziness. So I'll leave you there with that thought. And until next time, happy gate driver power supply enabling.